Hi everyone, Mr. Lee here. In this video, we're going to go over the Buggy Lab. Let's begin. So from the Buggy Lab, all groups should have gotten a graph that looks something like this, where we have a position versus time graph, like there, position versus time graph, where we have position in the y-axis and we have time in the x-axis. Remember, in terms of variables, um, position is used as a x and time is used as t. And the units for position for us will always be in meters, and the units for time for us will always be in seconds. And of course, the title for our graph is always in the y versus the x-axis, and our y-axis variable is position, and our x-axis is time. Okay, so when you plotted your points and you tried to create a line of best fit, you all should have gotten a line that looks something like this. Okay, now I want to pause right there and actually define a proper term to describe this line. We call this a linear line. And that's a term that we'll see throughout the year, and it actually tells us a lot of information. Um, One other thing that you had to find was the slope of this line. And for the sake of this video, I'm just going to make up a slope. So let's say that the slope for our linear line was 0.25 meters per second. And yes, your slope values should always have units no matter what. And this is because our units, believe it or not, tell us that we are looking at velocity. Okay, so the units give us a little bit of insight, a little bit of clues as to what we are looking for our representation. Okay, another thing that I want us to get used to is the idea of verbalizing or verbal the slope. All right, so if I were to verbal this graph slope, I would say object started at the origin, um, and the object moved in the positive direction. Okay, and this is where the important part comes in. For every 1 second, the object or the buggy moved, you guessed it, 0.25 meters, okay, or 25 centimeters if we were in the units of centimeters. All right, so the reason why verbalizing the slope is very important is because it gives a narrative to what the graph represents, and from that graph, we could tell what exactly happened in the lab. Now, there will be times when you're trying to solve problems and you just don't know where to start yet. Oftentimes, starting off with the verbal is one of the most effective ways to start any type of problem. All right, now from this verbal, I could imagine exactly what happened in the lab. Okay, and so I'm just going to do a quick sketch of what happened during the lab to get this slope. So we had the buggy, and we put down a little post-it note at the start of the buggy. So here our time was 0 seconds, and every, let's say, 1 second, we put down another post-it note, right? Every 1 second, we put another post-it note. So notice here that my time values are increasing, but you should know that in between each post-it note was 1 second. Now, according to our verbal, it says for every 1 second, we moved 0.25 meters. So between post-it note 1 and post-it note 2, the distance between the two will be 0.25 meters. Between post-it note 2 and post-it note 3, that would be 0.25 meters. And we'll just do one more. Between post-it note 3 and post-it note 4, it will be another 0.25 meters. All right, but in terms of position, the first post-it note would be in 0 meters. The second one would be at 0.25 meters, okay? But the third post-it note, because we are looking at the position relative to the starting position, it wouldn't be 0.25, but rather 0.5 meters or half a meter. And the fourth post-it note will be 0.75 meters, and the last post-it note will be at 1 meter. Okay, and so this is what your lab would have looked like. And from that lab, we would have created a graph that looked something like that. And from the graph, we could also tell exactly what happened at the lab. And that is the object started at the origin, moved in the positive direction. For every 1 second, the object moved 0.25 meters. Okay, now we have everything in place to start off our journey with our very first physics equation. Before we do that, let's come up with a definition from what we just drew. Okay, so we can say, first off, that the change in position, okay, because we were changing position 0.25 meters every time, over the change in time, okay, this is the definition to velocity. Okay, change in position over the change in time is the definition of velocity. Now, if we were to do this in shorthand, we would say that change, we could represent the word change with a triangle. That triangle is a Greek letter called delta, so I'll put that off to the side. And delta simply means change. Now, for us in physics, change is a very specific definition. Change means the final whatever, so in our case, it'll be final position minus the initial. And in our situation, it'll be the initial position, okay? So it will be the change in position, which we represent as x, over the change in time, okay? So this is our very first definition for our physics course. So let's put a little box around that, and let's start that. Congratulations. We just started our journey. All right, now the definitions are nice, but oftentimes for us here in physics, we will need to have a formula. So let's see how we can come to the formula with this definition and with the graphs that we have created. All right, so I just want to remind ourselves, if that is our graph, I'm going to recreate that graph below so that we can reference it. We have a graph like this: position, time, units, important, and straight line. Boom. All right, so this is our graph. Now, hopefully you've learned in your math classes the formula for a line for a graph. Okay, so sometimes we call that the point slope formula. It looks something like this: y is equal to mx plus b. And let's define a couple of things. Y is the y-axis variable. M is the slope. X is the x-axis variable, not to be confused with position for this lab. And B is what we call the y-intercept. Okay, and so with this graph, we're actually able to use the slope point or point slope formula to come up with our very first physics formula. So y is our y-axis variable, and for this lab, our y-axis variable was position. So I'm going to write that there. So position is equal to the slope. If you remember, our slope was 0.25. Our x-axis was time. And we started at the origin, so our y-intercept would be 0. Okay, so our formula is position is equal to 0.2 times time. Now, that doesn't really tell us much, right? So let's replace that with our variables, where position is represented as x is equal to 0.2, and time is represented as t. All right, now I'm going to do one more thing right below it. We don't want the 0.2 because that's very specific for our lab. I'm going to replace that with our variable v t. And you're wondering to yourself, Mr. Lee, how did you get v for 0.2? Well, if you go back up here, we said that velocity is the change in position over the change in time, okay? Delta x over delta t. So whenever we have something that is the y-axis divided by the x-axis, what we're looking at is the slope. And for our Buggy Lab here, we said that the slope, okay, that we found here was the velocity. Okay, so that's how I was able to get one idea, transfer it to another. Now we have a formula right there, where position is equal to v times t. Ta-da! Now, that's actually not the final version of the formula that we will work with. If you noticed, this plus b, we haven't touched it yet, okay? Now, we haven't touched it yet because we started at the origin. But what if for our lab, we didn't start at the origin, but rather we started slightly beyond the origin. So instead of having a graph that looks like this, I'll do this in a different color, we had um, a line that looked something like this. All right there. All right, so if we had a line that started like this, now we do have a y-intercept. That y-intercept is right there. Now, in terms of the lab, what that y-intercept represents is our initial position. So draw a line right there. And for physics here, these are called subscripts, where we put them slightly below the variable, and that's like a adjective or modifier to the variable. So that O represents our initial. Sometimes you might see me write it as a I for initial, right? Or O for initial. So both are acceptable. Now, according to that red line, we can now have a better definition and a better formula for our position time graphs. And that would be x is equal to vt, okay? And if we were to just transfer this plus v over, we would say plus x initial. All right, now that looks really, really good, okay? And that will be a perfectly acceptable formula, but I want to take it a step further, okay? So that we can try to make all these connections there. What I'm going to do is I'm going to subtract our x initial to the other side. So we have x minus x initial is equal to v times t. Now, if you're following along, you might already see this coming, but x minus x initial, we actually define that over here, delta, okay, where delta is the final minus the initial. And so what we can rewrite here, if x is just the final position and x is our initial position, we can say delta x is equal to v times t. Now, for those of you with very discerning eyes, you can see that this formula here matches this definition that we came up there. The variables are just rearranged. And that's that. That is the post lab for the Buggy Lab. Let's go over a couple of the highlights. One, for a constant velocity object or an object that's moving with constant velocity, if you have a straight line or a linear line, the slope will always be linear. Okay, that allows us to tell it's moving a straight line, but the slope represents the velocity. Okay, it's important to be able to always verbalize what's happening in the graph. And we came up with a very first definition. This velocity is equal to the change in position over the change in time. And from that definition, we were even able to come up with a formula where our delta x, by the way, this does have a definition, delta x, that represents displacement. Okay, where it's the final position minus the initial position is equal to displacement. That's important to have. Is equal to the velocity times the time. And if you just rearrange those variables, we get velocity is equal to delta x over delta t. And that is, in fact, our definition. And our definition is, in fact, our formula. And there you go. That's that. I'll see you next time. Bye-bye.